Beyond the furthest reaches of human exploration, where sunlight fades to barely a whisper, and the familiar warmth of our star becomes nothing more than a distant memory, something extraordinary is happening. Right now, at this very moment, humanity's most distant ambassador to the cosmos is sending back information that's causing scientists to fundamentally reconsider everything they thought they knew about the boundary of our solar system. We're talking about Voyager 1, that remarkable machine launched back when disco was king and bell-bottoms were the height of fashion, still functioning after nearly half a century in the brutal void of space, still transmitting data across billions upon billions of miles, and still discovering phenomena that challenge our understanding of the universe itself. What Voyager 1 has detected out there in the cosmic darkness isn't just interesting. It isn't merely noteworthy. It's absolutely wild, completely unexpected, and profoundly important for our understanding of where our solar system ends and true interstellar space begins. The data streaming back from this intrepid explorer is painting a picture of a region far more complex, far more dynamic, and far more mysterious than anyone had anticipated. Scientists are poring over the readings with a mixture of excitement and bewilderment, because what they're seeing simply doesn't match up with the predictions made by our most sophisticated models. Let's set the stage properly here, because to truly appreciate the magnitude of what's being discovered, you need to understand just how remarkable Voyager 1's journey has been. Launched on the 5th of September 1977 from Cape Canaveral, Florida, this spacecraft was built during an era when computers had less processing power than your modern coffee maker. The entire spacecraft weighs about as much as a small car, stands roughly 10 feet tall, and carries a suite of scientific instruments that were cutting-edge technology when Richard Nixon was still dealing with the aftermath of Watergate. Yet here we are, decades later, and this technological marvel from the 1970s is still operational, still collecting data, and still expanding the boundaries of human knowledge. The mission was originally designed to last just 5 years. 5 years! That was the plan. The engineers who built Voyager 1 hoped it might survive long enough to complete flybys of Jupiter and Saturn, maybe snap a few pictures, gather some measurements, and then slowly succumb to the harsh environment of space as its power systems degraded and its instruments failed. But Voyager 1 had other ideas. This spacecraft has become the cosmic equivalent of that old pickup truck that just refuses to die. The one that keeps running long after every mechanic said it should be in the junkyard. Except instead of hauling groceries, it's hauling scientific discoveries across the galaxy. Now, Voyager 1 sits more than 15 billion miles from Earth. Wrap your mind around that number for a moment. 15 billion miles. That's so far that when engineers send a command to the spacecraft, it takes over 22 hours for that signal to reach it, traveling at the speed of light. And then it takes another 22 hours for any response to come back. We're talking about a round-trip communication time of nearly 2 days. Imagine trying to have a conversation with someone where you ask a question, then have to wait almost 2 full days before you get an answer. That's the reality of communicating with Voyager 1. But despite this incredible distance, despite the fact that the spacecraft is operating on power levels that are constantly declining, despite instruments that have endured radiation, cosmic rays, and the brutal cold of space for nearly 50 years, Voyager 1 continues to send back measurements that are rewriting our understanding of the cosmos, and what it's detecting right now, out there at the edge of our solar system's influence, is truly remarkable. To understand what's so wild about these new detections, we need to talk about where Voyager 1 actually is. The spacecraft isn't just floating around in empty space somewhere beyond the planets. It has crossed a boundary, a threshold, a cosmic frontier that represents one of the most significant transitions in the entire solar system. In August of 2012, Voyager 1 became the first human-made object to enter interstellar space. Let that sink in for a moment. We built something, we launched it into the heavens, and it traveled so far that it actually left the bubble of our sun's influence and entered the space between the stars. But here's where things get really interesting, and where our conventional understanding starts to break down. Scientists had long theorized about what this boundary region would be like. They called it the heliopause, this theoretical edge where the solar wind, that constant stream of charged particles flowing out from our sun, finally meets the interstellar medium the material that exists between star systems. They expected it would be relatively straightforward, a clear demarcation between here and there, between our solar system and the galaxy beyond. They were wrong, spectacularly wrong. The heliopause, as Voyager 1 has discovered, is not a simple boundary at all. It's a complex, turbulent, dynamic region where two fundamentally different environments collide and interact in ways that nobody predicted. Imagine standing at the shore of an ocean, watching waves crash against the beach. Now imagine that same beach, but instead of water and sand, you've got solar wind particles and interstellar plasma. And instead of a gentle slope, you've got a boundary region that stretches across billions of miles, pulsing and shifting and churning with energies that could power entire civilizations. The latest data from Voyager 1 reveals that this boundary isn't stable. It's not sitting there quietly marking the edge of our solar system like some cosmic property line. Instead, it's moving. It's fluctuating. It's doing things that have scientists scratching their heads and going back to their calculations to figure out what's going on. The spacecraft's instruments have detected waves, oscillations in the magnetic fields and particle densities that suggest this region is far more active than anyone anticipated. What makes this even more fascinating is that these fluctuations appear to be responding to activity on the Sun, despite the fact that Voyager 1 is so far away that sunlight takes over 20 hours to reach it. The Sun goes through cycles of activity, periods where it's relatively quiet and periods where it's actively churning out massive solar flares and coronal mass ejections. These events send shock waves rippling outward through the solar system at tremendous speeds. And now, scientists are detecting evidence that these shock waves are still influencing conditions at the heliopause, billions of miles from their source. Think about what that means. An event that happens on the surface of our Sun, 93 million miles from Earth, can send effects cascading outward across the entire solar system, past all the planets, past the Kuiper Belt, past the scattered disk objects, all the way out to where Voyager 1 is exploring, and still have a measurable impact. The Sun's influence extends farther and penetrates deeper into space than we ever imagined. Our solar system, it turns out, is a much larger and more interconnected place than we thought. But the wild discoveries don't stop there. Voyager 1 has also detected something that has planetary scientists particularly excited and puzzled. The spacecraft's cosmic ray detector, an instrument designed to measure high-energy particles from beyond our solar system, has been registering some truly bizarre readings. The cosmic ray levels aren't constant. They're not gradually increasing as Voyager moves deeper into interstellar space. Instead, they're fluctuating in ways that suggest something unexpected is happening with how these particles are being filtered or accelerated at the boundary region. Cosmic rays are some of the most energetic particles in the universe. Atomic nuclei that have been accelerated to tremendous speeds by supernova explosions, neutron stars, black holes, and other exotic cosmic phenomena. When they enter our solar system, they encounter the solar wind, which acts like a kind of shield, deflecting some of them and reducing their intensity. Scientists expected that once Voyager 1 crossed into interstellar space, cosmic ray levels would increase and then stabilize, since the spacecraft would be beyond the protective bubble of the solar wind. That's not what's happening. The cosmic ray measurements are showing variations that suggest the boundary region itself is somehow processing these particles, either accelerating some of them or creating conditions that affect how they propagate through space. Some readings show sudden spikes in cosmic ray intensity, followed by equally sudden drops. Others show gradual increases that then plateau before dropping again. The pattern doesn't match any of the predicted models, and it's forcing scientists to reconsider their fundamental understanding of how matter and energy behave at the edges of stellar influence. One of the most intriguing hypotheses being explored is that the heliopause might be generating its own unique phenomena. When two different plasmas meet, when particles from the solar wind collide with particles from the interstellar medium, they don't just bounce off each other like billiard balls. They interact electromagnetically, creating magnetic fields, generating electric currents, and potentially accelerating particles to high energies. The boundary region might essentially be acting like a giant natural particle accelerator, taking relatively low-energy particles and boosting them to tremendous speeds. If this turns out to be true, it would be absolutely revolutionary for our understanding of how stellar systems interact with the galaxy around them. Every star has a region like this, a boundary where its influence meets the interstellar medium. If these boundaries are generating high-energy particles, they could be contributing to the overall cosmic ray background in ways we never considered. They could be affecting the evolution of nearby molecular clouds, influencing star formation, and playing a role in the complex dance of matter and energy that shapes galaxies. The magnetic field data coming from Voyager 1 is equally fascinating and equally puzzling. Scientists expected that when the spacecraft crossed the heliopause, there would be a dramatic change in the magnetic field orientation. Inside the heliosphere, the region dominated by the Sun's magnetic influence. The magnetic field lines are connected to the Sun, shaped by the solar wind and the Sun's rotation. Outside the heliosphere, in interstellar space, the magnetic field should be aligned with the galactic magnetic field, pointing in an entirely different direction. Voyager 1 did detect a change in magnetic field strength when it crossed the boundary, but the field direction didn't change in the way scientists expected. Instead of rotating to align with the predicted galactic field, the magnetic field in interstellar space appeared to be running roughly parallel to the heliopause itself. This was completely unexpected and suggested that the boundary region has a much stronger influence on the local magnetic environment than anyone thought possible. Even more mysteriously, subsequent measurements have shown that this magnetic field orientation isn't constant either. It appears to be shifting, rotating slightly over time, as if the boundary region is itself in motion, or as if there are large-scale magnetic structures in interstellar space that Voyager 1 is gradually moving through. Each new data transmission reveals another layer of complexity, another piece of evidence that the space around us is far more structured and dynamic than our models predicted. Now, you might be wondering why any of this matters. Why should we care about magnetic fields and particle densities in a region of space so far from Earth that it takes light nearly a day to traverse the distance? What possible relevance could this have to our lives here, on our comfortable planet, orbiting our stable star, protected by our magnetic field and our thick atmosphere? The answer is both profound and humbling. Understanding the boundary of our solar system, understanding how our sun's influence interacts with the galaxy, is crucial for comprehending our place in the cosmos. We live in a dynamic universe where energy and matter are constantly flowing, constantly interacting, constantly changing. The discoveries Voyager 1 is making aren't just about some distant region of space. They're about understanding the fundamental processes that govern how stellar systems form, evolve, and interact with their galactic environment. Consider this: our solar system is moving. Right now, at this very moment, our Sun and all the planets are racing through space at about 450,000 miles per hour relative to the surrounding stars. We're on a cosmic journey that will take us through different regions of the galaxy, regions with different densities of interstellar material, different magnetic field strengths, different levels of cosmic radiation. The heliopause, that boundary region Voyager 1 is exploring, is our shield against these changing galactic conditions. It deflects cosmic rays, it filters out some of the interstellar material, and it creates a relatively stable environment within which life on Earth can flourish. But the heliopause isn't constant. As our solar system moves through the galaxy, as we encounter regions of higher or lower density, the heliopause expands and contracts, strengthens and weakens. Understanding how it behaves, understanding what happens at this crucial boundary, helps us predict how conditions within our solar system might change in the future. Will Earth's radiation environment remain stable? Will the flux of cosmic rays hitting our atmosphere increase or decrease? These aren't idle academic questions. Cosmic rays can affect atmospheric chemistry, cloud formation, and possibly even climate patterns. The wild discoveries from Voyager 1 are also revealing something even more fundamental about the nature of boundaries in space. We humans like to think in terms of clear divisions, distinct separations between one thing and another. We draw borders on maps, we erect fences between properties, we categorize and classify and compartmentalize. But the universe doesn't work that way. The boundary between our solar system and interstellar space isn't a line. It's a region, a zone of transition that extends across vast distances and exhibits behaviors that are unique to that transitional state. This is a concept that appears again and again in astrophysics. The boundary between a star and space isn't the star's visible surface, but rather an extended atmosphere that gradually fades into the vacuum. The boundary between a planet and space isn't a hard edge, but rather an atmosphere that gradually thins until individual molecules are so far apart that they rarely interact. The boundary between galaxies isn't empty space, but rather a complex environment filled with gas, dust, and dark matter. Boundaries in the universe are regions, not lines, and understanding them requires thinking in terms of gradients and transitions rather than sharp divisions. What Voyager 1 is teaching us is that these transitional regions are often the most interesting places to study, because it's in these zones where different physical processes collide and interact, creating phenomena that wouldn't exist in either of the regions being separated. The heliopause is revealing itself to be one of these special places, a laboratory where we can study how plasmas of different origins interact, how magnetic fields reconnect and reconfigure, how particles are accelerated to high energies, all in an environment that we could never replicate on Earth or even in Earth orbit. Scientists are now racing to analyze every bit of data coming from Voyager 1, knowing that the spacecraft's power supply is gradually declining and that within a few years, possibly by the late 2020s, the spacecraft will no longer have enough power to operate its scientific instruments. Every transmission could potentially be one of the last. Every new measurement is precious, irreplaceable, a gift from a machine that has exceeded every expectation and survived far longer than anyone dared to hope. The engineering challenges involved in maintaining contact with Voyager 1 are themselves remarkable. The spacecraft transmits with a power of about 23 watts, less than a typical LED light bulb. By the time that signal reaches Earth, having spread out across billions of miles of space, it's incredibly weak. NASA's Deep Space Network, an array of massive radio antennas located in California, Spain, and Australia, must strain to detect these faint whispers from the edge of the solar system. The fact that we can still communicate with Voyager 1 at all is a testament to the ingenuity of the engineers who designed both the spacecraft and the ground systems that support it. And yet, despite all the challenges, despite the vast distances and the declining power and the aging instruments, Voyager 1 continues to deliver discoveries. Each data transmission is carefully analyzed by teams of scientists who have devoted their careers to understanding the data from this remarkable mission. They build models, run simulations, compare the measurements to predictions, and slowly piece together a picture of what's happening out there at the boundary of our cosmic neighborhood. What they're finding is that the solar system is a far more complex and interesting place than anyone imagined back in 1977 when Voyager 1 was launched. The simple model of a sun, surrounded by planets orbiting in neat circles, all enclosed in a bubble that separates us from the rest of the galaxy, has given way to a much more nuanced understanding. Our solar system is a dynamic, evolving environment, shaped by the interplay between our sun's activity and the galactic medium through which we're traveling. The heliopause breathes in and out, responding to solar cycles and to changes in the interstellar environment. Magnetic fields twist and reconnect, creating structures that persist across vast regions of space. Particles are accelerated, decelerated, deflected, and absorbed in a complex dance of electromagnetic forces. The density measurements that Voyager 1 is transmitting back to Earth are revealing another layer of this cosmic puzzle that has scientists absolutely captivated. When the spacecraft first crossed the heliopause back in 2012, instruments detected a dramatic increase in the density of plasma, the ionized gas that fills the space between stars. This made perfect sense. Inside the heliosphere, the solar wind has blown a bubble in the interstellar medium, creating a region of relatively low density. Outside that bubble, in interstellar space proper, the density should be higher. And indeed, that's exactly what Voyager 1 measured when it first made the crossing. But here's where things get wild. The density isn't remaining constant. Instead, Voyager 1 has detected fluctuations in the plasma density that suggest the spacecraft is moving through structures in the interstellar medium itself. These aren't random variations. They show patterns, periodicities, evidence of organization on scales that span light years. What could possibly create such structures in the supposedly uniform void between the stars? The answer, scientists are discovering, is that interstellar space isn't uniform at all. It's filled with clouds, filaments, sheets, and voids, a cosmic foam of material left over from ancient supernova explosions, stellar winds from other stars, and the slow churning of galactic dynamics. Our solar system is currently passing through what astronomers call the local interstellar cloud, sometimes referred to as the local fluff, a region of slightly higher density within the larger local bubble, which itself is a cavity in the interstellar medium created by supernova explosions millions of years ago. The local interstellar cloud isn't particularly dense by cosmic standards. It contains maybe a few thousand atoms per cubic inch, compared to the billions upon billions that make up even the thinnest wisps of Earth's upper atmosphere. But it's denser than the local bubble that surrounds it, and Voyager 1's measurements are revealing the internal structure of this cloud in unprecedented detail. The spacecraft has detected regions where the density spikes upward, suggesting it's encountering denser clumps or knots in the cloud. It's detected regions where the density drops, suggesting holes or voids in the structure. And crucially, it's detecting changes in density that correlate with changes in other properties like magnetic field strength and cosmic ray intensity. These correlations are telling scientists that the structures in the interstellar medium aren't just random fluctuations, but are organized by physical processes, shaped by magnetic fields and pressure gradients, and the flow of material through the galaxy. Think about what this means for our understanding of the galaxy as a whole. For decades, astronomers have studied the interstellar medium using telescopes that observe light from distant stars, looking at how that light is absorbed or scattered by intervening material. These observations have revealed a great deal about the average properties of interstellar space, but they can't capture the fine-scale structure, the detailed variations that exist on scales of billions or tens of billions of miles. Voyager 1 is providing the first in-situ measurements, the first direct sampling of this material, and it's showing us that the interstellar medium is far more textured and complex than telescopic observations alone could reveal. This has profound implications for understanding how stars and planets form. Stars are born in dense regions of the interstellar medium, where gravity can overcome the outward pressure of gas and pull material together into collapsing clouds. The structure and organization of the interstellar medium determines where and when stars can form, how much material is available for planet formation, and what kind of chemical elements those planets will contain. By revealing the detailed structure of the local interstellar cloud, Voyager 1 is helping us understand the environment in which future generations of stars and solar systems will form in our region of the galaxy. But let's return to the heliopause itself, because the boundary region continues to yield surprises that challenge our theoretical models. One of the most unexpected discoveries involves what scientists call plasma oscillations, or waves. Plasma, that state of matter where electrons have been stripped from atoms creating a soup of charged particles, can support various types of waves. Oscillations where density and electromagnetic fields vary in coordinated patterns that propagate through space, much like sound waves propagate through air. Voyager 1's plasma wave instrument has detected these oscillations at frequencies and amplitudes that weren't predicted by pre-mission models. The waves appear to be generated by instabilities at the heliopause itself, places where the smooth flow of the solar wind colliding with the interstellar medium becomes turbulent and chaotic. In these turbulent regions, energy cascades from large scales to small scales, creating eddies and vortices in the plasma that generate waves. These waves then propagate outward, carrying energy and information about conditions at the boundary to regions far removed from where they were generated. What makes these plasma waves particularly interesting is that they can interact with charged particles, accelerating some particles to high energies while decelerating others. This process, called wave-particle interaction, is believed to be one of the mechanisms responsible for creating the anomalous cosmic rays that Voyager 1 has been detecting. These aren't cosmic rays from supernova explosions or distant galaxies. They're particles that originated in our own solar system, either from the solar wind itself or from neutral atoms in the interstellar medium that became ionized when they entered the heliosphere. These particles get caught up in the turbulent processes at the heliopause, bounced back and forth by magnetic fields and plasma waves, and gradually accelerated to energies far higher than they started with. The discovery of these locally accelerated particles has opened up an entirely new field of research. Scientists are now working to understand exactly how the acceleration process works, what determines the maximum energy these particles can reach, and how many of these particles are being produced. Some theoretical models suggest that the heliopause could be producing enough energetic particles to contribute significantly to the cosmic ray background in the outer solar system. If true, this would mean that our solar system isn't just a passive recipient of cosmic radiation from the galaxy, but is actually contributing to that radiation through processes happening at its own boundary. Temperature is another parameter that's proving to be far more complex than anticipated. When we talk about temperature in space, we're generally referring to the average kinetic energy of particles, how fast they're moving. In the solar wind, particles are hot, moving at speeds of hundreds of miles per second. In the interstellar medium, the temperature depends on what component you're measuring. The electrons might have a different temperature than the ions, and different ion species might have different temperatures. It's not like measuring the temperature of air on Earth where everything is in thermal equilibrium. Voyager 1 has measured temperatures in interstellar space that don't quite match predictions. The plasma appears to be cooler than some models suggested, but hotter than others predicted. More puzzlingly, there's evidence that the temperature varies with location, increasing in some regions and decreasing in others. These variations could be due to heating from plasma waves, cooling from expansion as the plasma flows through space, or compression and rarefaction caused by large-scale flows in the interstellar medium. Untangling these different effects requires careful analysis and sophisticated modeling work that's still ongoing as new data continues to arrive. The radiation environment that Voyager 1 is experiencing has also proven to be more hostile than mission planners originally anticipated. The spacecraft's electronics were designed to withstand a certain level of radiation exposure, based on estimates of what the radiation environment would be like in the outer solar system and beyond. But the cumulative dose of radiation that Voyager 1 has received over its nearly 50-year mission has been higher than expected, partly because the cosmic ray flux is higher than models predicted, and partly because the spacecraft has simply survived so much longer than anyone dared to hope. This radiation exposure has taken its toll. Some of the spacecraft's instruments have experienced degradation, showing increasing noise levels and decreasing sensitivity as radiation damage accumulates in their electronic components. Engineers have had to develop clever workarounds, adjusting calibration parameters, using redundant systems, and sometimes relying on correlations between different instruments to extract reliable data from degraded sensors. It's a constant battle against entropy, against the inexorable wearing down of systems that have been operating far longer than they were ever designed to function. Yet somehow, Voyager 1 keeps working. The spacecraft carries 3 radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity. When Voyager 1 launched, these generators produced about 470 watts of electrical power. Today, after decades of decay, they produce roughly 220 watts, and that number decreases by about 4 watts every year. As power levels decline, mission managers have had to make difficult decisions about which instruments to shut down and which to keep running. Several instruments have already been turned off to conserve power, and eventually there won't be enough electricity to run any of the science instruments. The current estimates suggest that Voyager 1 will have enough power to operate at least one scientific instrument until approximately 2025 or possibly into the late 2020s, depending on how efficiently the remaining power can be managed. After that, the spacecraft will continue to coast through interstellar space, silent and dark, a monument to human ingenuity and curiosity. Carrying its famous golden record with sounds and images of Earth toward stars, it will reach in tens of thousands of years. But for now, while it still has power, while it can still communicate, Voyager 1 continues its mission of discovery, continues to probe the mysteries of the boundary between our solar system and the galaxy beyond. The implications of Voyager 1's discoveries extend far beyond our immediate stellar neighborhood. Every star has a heliosphere, a region of space dominated by its stellar wind. Understanding how our sun's heliosphere works, how it interacts with the interstellar medium, provides insights into how other stellar systems behave. This is particularly relevant for understanding the environments around other stars that might host planets, possibly even planets with life. Consider a star system located in a denser region of the galaxy, where the interstellar medium contains more material and exerts more pressure on the stellar wind. Such a star's heliosphere might be compressed, smaller than our sun's, meaning that any planets in that system would be exposed to higher levels of cosmic radiation. Alternatively, consider a more active star, one that produces a stronger stellar wind. That star's heliosphere might be larger, providing better shielding for its planets, but also subjecting those planets to stronger particle radiation from the stellar wind itself. There's a delicate balance involved, and understanding that balance is crucial for assessing the habitability of exoplanets. Voyager 1's measurements are providing the ground truth, the actual data against which theoretical models of stellar heliospheres can be calibrated and tested. When astronomers build computer simulations of how stellar winds interact with the interstellar medium around other stars, they can now compare those simulations to real measurements from our own heliosphere. This dramatically improves confidence in the models and allows for more accurate predictions about conditions in other stellar systems. The magnetic reconnection events that Voyager 1 has detected in the boundary region are particularly fascinating from a theoretical standpoint. Magnetic reconnection is a process where magnetic field lines that are pointing in opposite directions come together, break, and reconnect in a new configuration. This process converts magnetic energy into kinetic energy and heat, accelerating particles and generating powerful jets of plasma. Magnetic reconnection is responsible for solar flares, for aurora on Earth, for explosive events in the magnetospheres of planets, and apparently for some of the dynamics happening at the heliopause. The evidence for magnetic reconnection at the heliopause comes from sudden changes in magnetic field direction, coincident with spikes in particle energies and plasma density. These signatures match what scientists observe during reconnection events in other contexts, suggesting that the same fundamental process is at work. But studying reconnection at the heliopause is particularly valuable because it's happening in a regime where the plasma is much more tenuous than in most other reconnection sites we can study. The density is lower, the magnetic fields are weaker, and the spatial scales are enormous. This allows scientists to test whether their understanding of magnetic reconnection, developed primarily through studies of denser plasmas, holds true in these extreme conditions. So far, the answer appears to be yes, but with interesting caveats. The reconnection events at the heliopause seem to proceed more slowly than equivalent events in denser plasmas, which makes sense given that there are fewer particles available to carry current and facilitate the process. But the overall structure of the events, the way magnetic fields reconfigure, and the way particles are accelerated, follows patterns consistent with reconnection theory. This is providing valuable confirmation that our understanding of this fundamental plasma process is robust across a wide range of conditions. The turbulence that Voyager 1 is detecting in the boundary region represents another frontier in plasma physics research. Turbulence is one of the great unsolved problems in classical physics, a phenomenon that's easy to observe but devilishly difficult to describe mathematically. When a fluid or plasma becomes turbulent, its motion transitions from smooth and predictable to chaotic and irregular, with energy cascading from large eddies to progressively smaller ones until it's finally dissipated as heat. The details of how this cascade works, what determines the properties of the turbulence, and how turbulence affects the transport of energy and particles are all active areas of research. The heliopause provides a natural laboratory for studying plasma turbulence in conditions very different from what we can achieve in laboratories on Earth, or even in near-Earth space. The turbulence appears to be driven by the shear between the solar wind and the interstellar medium, two flows moving at different speeds and in different directions. This creates instabilities that grow into turbulent eddies, which then break down into smaller structures. Voyager 1's instruments can measure the properties of this turbulence, providing data that helps validate and refine theoretical models. One particularly intriguing aspect of the turbulence is that it appears to be anisotropic, meaning its properties depend on direction. In isotropic turbulence, eddies are equally likely to occur in any direction, and the statistical properties of the turbulence are the same whether you measure them along the x-axis, y-axis, or z-axis. But in the presence of a strong magnetic field, which is the case at the heliopause, turbulence tends to become stretched along the field lines, creating elongated structures rather than symmetric eddies. Voyager 1's measurements are providing evidence for this anisotropy, showing that the magnetic field is playing a crucial role in organizing the turbulent motions. The duration of Voyager 1's mission allows for observations of long-term trends that would be impossible with a shorter mission. Scientists can now track how conditions at the heliopause change over years and even decades, watching how the boundary responds to solar cycles and to changes in the interstellar medium. This long-term perspective is revealing that the heliopause is not static, but is constantly adjusting, constantly evolving in response to changing conditions on both sides of the boundary. For example, the Sun goes through an 11-year activity cycle, with periods of high activity characterized by many sunspots and frequent solar flares, alternating with periods of low activity where the Sun's face is relatively blank and quiet. During high activity periods, the solar wind is stronger and more variable, containing more high-speed streams and more coronal mass ejections. This increased activity pushes the heliopause outward, expanding the heliosphere. During low activity periods, the solar wind weakens, and the pressure from the interstellar medium pushes the heliopause inward, shrinking the heliosphere. Voyager 1 has now been in interstellar space through parts of multiple solar cycles, allowing scientists to observe how the boundary region responds to these cyclic changes in solar activity. The data shows that disturbances from the Sun can take years to propagate all the way out to the heliopause, creating a complex pattern of waves and oscillations in the boundary position. Some of these disturbances appear to steepen into shocks as they propagate, creating sudden jumps in density and magnetic field strength when they finally reach Voyager 1's location. The spacecraft has actually detected several of these transient shocks, sudden increases in plasma density and magnetic field strength that last for a period of time before subsiding. Each shock represents the arrival of a disturbance that originated in some solar event years earlier, a coronal mass ejection, or a particularly strong solar wind stream that sent a pressure wave rippling outward through the heliosphere. By the time these waves reach the heliopause, they've traveled for years, been modified by their interaction with the solar wind and the interstellar medium, and contain information about conditions throughout the entire heliosphere. Analyzing these transient events is like doing heliospheric archaeology. Scientists can work backward from the properties of the shock Voyager 1 detects, using models of wave propagation and evolution to infer what the original solar disturbance must have been like and what conditions it encountered during its multi-year journey to the heliopause. This provides a way to probe regions of the heliosphere that Voyager 1 never directly passed through, using the waves as messengers carrying information from those distant regions. The neutral atoms that Voyager 1 is detecting represent yet another piece of the puzzle. Not all the material in space is ionized plasma. There are also neutral atoms, particles that haven't lost their electrons and therefore don't respond to electric and magnetic fields the way charged particles do. These neutral atoms can flow freely through the heliopause, unaffected by the magnetic barriers that deflect charged particles. When a neutral atom from the interstellar medium enters the heliosphere, it can eventually become ionized by ultraviolet light from the Sun or by collisions with solar wind particles. Once ionized, it becomes picked up by the solar wind and carried along with the flow. This process of neutral atoms entering the heliosphere, becoming ionized, and then being swept up by the solar wind, is one of the mechanisms by which interstellar material enters our solar system. Voyager 1's measurements of neutral atom densities help quantify how much material is entering through this pathway. The data suggests that significant amounts of interstellar helium, hydrogen, and other elements are constantly streaming into the heliosphere, adding to the complexity of the particle populations in the outer solar system. Some of these neutral atoms don't make it all the way to the inner solar system. They get ionized in the outer heliosphere and then swept back out toward the heliopause by the solar wind. When they reach the boundary region, they can pile up, creating enhanced densities of what are called pickup ions. These pickup ions can then be further accelerated by the processes happening at the heliopause, potentially contributing to the anomalous cosmic rays that Voyager 1 detects. It's a complex cycle of material flowing in, being processed, and flowing back out, all mediated by the intricate dance of neutral atoms and charged particles at the boundary of our solar system. The instrumentation aboard Voyager 1 represents a masterpiece of 1970s engineering, and understanding what these instruments are actually measuring helps illuminate just how remarkable the spacecraft's discoveries truly are. The plasma science instrument, for instance, was designed to measure the velocity, density, and temperature of charged particles in the solar wind and beyond. It consists of 4 cup-shaped sensors that collect ions and electrons, measuring their energy and direction of travel. When Voyager 1 crossed into interstellar space, This instrument detected the dramatic change in plasma properties that confirmed the spacecraft had indeed left the heliosphere behind. However, the plasma science instrument stopped functioning properly in 1980, shortly after the Saturn encounter, when its primary sensor could no longer rotate to point in the right direction. Since then, scientists have had to rely on other instruments to infer plasma properties, using clever indirect methods to extract information about the plasma environment from measurements of magnetic fields and plasma waves. It's a testament to the ingenuity of the mission scientists that they've been able to continue characterizing the plasma environment for more than 4 decades, despite the loss of their primary plasma instrument so early in the plasma instrument omission. The magnetometer instrument, on the other hand, has continued to function beautifully throughout the entire mission. This instrument measures the strength and direction of magnetic fields using 2 sets of sensors mounted on a boom extending out from the spacecraft body. The boom is necessary to keep the sensors away from the spacecraft's own magnetic fields, which would otherwise contaminate the measurements. Every 96 seconds, the magnetometer takes a reading, building up a detailed picture of how the magnetic field varies as Voyager 1 moves through space. It's this instrument that detected the lack of rotation in the magnetic field direction when Voyager 1 crossed the heliopause, the puzzling observation that challenged scientists' expectations and revealed new complexities in how the boundary region is structured. The cosmic ray subsystem consists of several detectors designed to measure high-energy particles from various sources. Some sensors measure the intensity of cosmic rays as a function of their energy and direction. Others can identify the specific atomic nuclei that make up the cosmic rays, distinguishing between hydrogen, helium, carbon, oxygen, and heavier elements. Still others measure electrons and the isotopic composition of certain elements. Together, these sensors provide a comprehensive picture of the energetic particle environment, revealing not just how many particles are present, but where they came from and how they've been processed by their journey through the galaxy and the heliosphere. It's the cosmic ray subsystem that has detected the wild fluctuations in particle intensity that have so puzzled scientists. The readings show that Voyager 1 is in an environment where cosmic ray intensity can change significantly over relatively short periods, sometimes increasing by 10 or 20% over the course of weeks or months, then decreasing again. These variations don't correlate in simple ways with other parameters like magnetic field strength or plasma density, suggesting that multiple processes are affecting cosmic ray propagation in this region. The low-energy charged particle instrument adds another layer of information, measuring particles with energies lower than those detected by the cosmic ray subsystem, but higher than the thermal plasma particles. These are the anomalous cosmic rays and other intermediate energy particles that are being accelerated somewhere in the heliosphere or at its boundary. By measuring their energy spectra and how those spectra change over time, scientists can learn about the acceleration mechanisms at work and how efficiently the heliopause is producing these energetic particles. The plasma wave subsystem is perhaps the most aurally interesting instrument on the spacecraft. It measures electric fields oscillating at frequencies ranging from a few hertz up to about 56 kilohertz, covering the range from very low-frequency waves up into what would be audible sound if these were acoustic waves in air rather than electromagnetic waves in plasma. Scientists have actually taken the data from this instrument and converted it into sound files that you can listen to, creating an eerie symphony of whistles, hisses, and static that represents the electromagnetic environment around Voyager 1. These sounds are the voices of plasma waves, the acoustic emissions from magnetic reconnection events, the signatures of shocks passing by the spacecraft. One particularly dramatic event occurred in 2012, shortly after Voyager 1 crossed the heliopause. The plasma wave instrument detected a strong oscillation lasting for several months, a clear tone at a specific frequency that scientists could use to calculate the plasma density. This was actually how they confirmed that Voyager 1 had entered interstellar space, by showing that the plasma density had increased to levels consistent with being outside the heliosphere. Since then, the instrument has detected several more of these oscillations, each one providing a snapshot of the local plasma density and revealing how that density changes as Voyager 1 continues its journey. Beyond the scientific instruments, Voyager 1 carries several engineering subsystems that are themselves remarkable for their longevity. The spacecraft's computers, for instance, use technology that predates the microprocessor revolution. The flight data system, which manages the collection and transmission of scientific and engineering data, has a whopping 67 kilobytes of memory. That's kilobytes, not megabytes or gigabytes. The entire memory capacity of Voyager 1's computers is less than the size of a typical email message today. Yet this ancient hardware continues to execute its programming flawlessly, managing complex sequences of commands, collecting data from multiple instruments, and coordinating the transmission of information back to Earth. The attitude control system, which keeps Voyager 1 oriented properly in space, relies on thrusters that fire tiny bursts of hydrazine fuel to make adjustments to the spacecraft's rotation. After nearly 50 years, these thrusters are still functioning, though they've degraded over time and now require longer firing times to produce the same amount of thrust. In 2017, engineers successfully fired a set of backup thrusters that hadn't been used since 1980, demonstrating that even dormant systems can be revived when needed. The spacecraft carries a limited supply of fuel, and conserving that fuel is crucial to maintaining proper orientation for as long as possible. The radio transmitter that sends data back to Earth operates at a frequency of about 8.4 gigahertz in the X-band portion of the radio spectrum. The transmitted signal, as mentioned earlier, is incredibly weak by the time it reaches Earth, requiring the massive antennas of the deep space network to detect it. But the signal carries an enormous amount of information, encoded in a carefully designed format that allows for error, correction, and verification. Even when the signal is so weak that it's barely distinguishable from background noise, sophisticated signal processing techniques can extract the data with remarkable reliability. The data rate from Voyager 1 has decreased over the years as the spacecraft has moved farther from Earth and the signal has grown weaker. Currently, Voyager 1 transmits at about 160 bits per second, roughly the same as a dial-up modem from the 1990s. This incredibly slow data rate means that transmitting even a modest amount of information takes considerable time. A single image from Voyager's cameras, back when they were still operational, took hours to transmit. Scientific data is compressed and prioritized, with the most important measurements sent first, and less critical data queued up for transmission when communication windows allow. Speaking of the cameras, Voyager 1's imaging system was shut down in 1990, shortly after taking the famous pale blue dot photograph of Earth from beyond Neptune's orbit. The cameras were no longer needed for the extended interstellar mission, and shutting them down saved precious power for the instruments that could still make useful measurements in the outer solar system and beyond. That final image, showing Earth as a tiny speck of light suspended in a shaft of scattered sunlight, remains one of the most poignant and humbling photographs ever taken, a reminder of our planet's fragility and isolation in the vast cosmos. The challenges of maintaining Voyager 1 extend beyond just the spacecraft itself. Here on Earth, the deep space network that communicates with Voyager is itself aging and requires constant maintenance and upgrades. The 70-meter antennas used to communicate with Voyager 1 are massive structures, among the largest steerable antennas in the world, and they need to be precisely pointed to receive the faint signals from the distant spacecraft. The network is shared among numerous space missions, and scheduling time for Voyager observations must be balanced against the needs of other spacecraft exploring Mars, Jupiter, Saturn, and beyond. The team of engineers and scientists who manage the Voyager mission has changed considerably over the decades. The young engineers who launched Voyager 1-inch 1977 are now retired, and the mission is being run by people who weren't even born when the spacecraft began its journey. This transfer of knowledge across generations is itself a remarkable achievement, requiring careful documentation of the spacecraft systems, the quirks and peculiarities that have emerged over decades of operation, and the institutional memory of how to troubleshoot problems when they arise. And problems do arise. In 2022, Voyager 1 began sending back telemetry data that didn't make sense, indicating impossible positions and orientations for the spacecraft. Engineers eventually traced the problem to a corrupted memory location in the attitude control system. A single bit flipped from 0 to 1, or vice versa, probably due to a cosmic ray impact. They were able to work around the problem by switching to backup hardware, demonstrating once again the resilience of the spacecraft's design and the skill of the engineering team managing it. The discoveries Voyager 1 is making about the heliopause have implications that reach into the realm of astrobiology, the study of life in the universe. One of the factors that determines whether a planet can host life is its radiation environment. Too much radiation can damage biological molecules, making it difficult for life to emerge or persist. Earth is protected from cosmic radiation by its magnetic field and atmosphere, but the heliosphere provides an additional layer of shielding, deflecting some of the galactic cosmic rays before they even reach the inner solar system. Understanding how effective this shielding is and how it varies over time helps scientists assess the radiation environments on planets in our solar system and potentially around other stars. Mars, for instance, lacks a strong magnetic field and has a thin atmosphere, making it much more vulnerable to cosmic radiation than Earth. The intensity of cosmic radiation at Mars depends partly on how much shielding the heliosphere provides, and that shielding varies with the solar cycle and with the properties of the interstellar medium the solar system is moving through. Voyager 1's measurements of cosmic ray intensity in interstellar space provide a baseline, showing what the radiation environment would be like without any heliospheric shielding at all. By comparing measurements from Voyager 1-inch interstellar space with measurements from other spacecraft in the inner solar system, scientists can quantify how much shielding the heliosphere provides and how that shielding changes under different conditions. This information is directly relevant for planning human missions to Mars and beyond, as astronauts traveling through interplanetary space will be exposed to higher radiation levels than they experience on Earth. The heliosphere also plays a role in determining what kind of material reaches the inner solar system. Interstellar dust grains, tiny particles of solid material that float through the galaxy, can potentially penetrate the heliosphere and reach the inner planets. Some of these dust grains may contain organic molecules or even primitive building blocks of life, material that could have been delivered to young Earth during its formation. Understanding how efficiently the heliosphere filters out or admits these dust grains is part of understanding the delivery of prebiotic material to planets. Voyager 1 doesn't carry a dedicated dust detector, but scientists can infer something about the dust environment from other measurements. Impacts from dust grains can sometimes be detected as transient signals in the plasma wave instrument, as the impact vaporizes a tiny bit of the spacecraft's surface and creates a momentary cloud of ionized material. The frequency and intensity of these signals can provide rough estimates of the dust density and the size distribution of the grains. The temperature structure of the heliosphere and the boundary region is also relevant for understanding the thermal history of objects in the outer solar system. Small bodies like comets, asteroids, and Kuiper belt objects are influenced by the thermal environment around them, which affects how volatiles like water, ice, and frozen gases behave on their surfaces. The heliosphere creates a region where solar heating dominates, but beyond the heliopause, these objects would be exposed only to the faint glow of starlight and the cosmic microwave background, creating very different thermal conditions. Voyager 1's measurements of temperature in interstellar space, while complicated by the fact that different particle species can have different temperatures, provide information about this outer thermal environment. The data suggests that interstellar plasma is indeed significantly cooler than the solar wind, which makes sense given that it's not being heated by a nearby star. But the exact temperatures and how they vary with location are still being worked out, requiring careful analysis of the available data and comparison with theoretical models. One of the most philosophically profound aspects of Voyager 1's mission is that it represents humanity's first step into the galaxy proper. Every human who has ever lived, every civilization that has ever existed, every structure we've built, and every journey we've undertaken has occurred within the protective bubble of the heliosphere. Voyager 1 has now ventured beyond that bubble, becoming our first ambassador to the wider galactic community. The spacecraft carries the Golden Record, a compilation of sounds, images, and information about Earth and humanity intended as a message to any extraterrestrial intelligence that might someday encounter the spacecraft. The chances of the Golden Record ever being found are vanishingly small. Space is unimaginably vast, and Voyager 1 is an incredibly tiny object moving through that vastness. It will take about 40,000 years for the spacecraft to pass anywhere near another star system, and even then, it will still be trillions of miles away from the nearest stellar neighbor. The record is more a symbolic gesture than a serious attempt at communication. A message in a bottle tossed into an ocean far larger than any ocean on Earth. But the symbolism is powerful. The very act of creating the record, of trying to summarize what makes humanity and Earth special, forced the creators to think deeply about who we are and what we want to say about ourselves. The record includes greetings in dozens of languages, Musical selections from cultures around the world, sounds of nature and human activity, and images showing the diversity of life and landscapes on Earth. It's a time capsule of Earth in the late 1970s, preserved on a golden disc that will likely outlast our entire civilization. Carl Sagan, who played a leading role in creating the golden record, described it as a message expressing hope that extraterrestrial civilizations exist and that humanity might someday join a galactic community of intelligent species. Whether such civilizations exist remains one of the great unanswered questions of science. Voyager 1's journey through interstellar space is, in a small way, the beginning of our search for an answer to that question. Every measurement the spacecraft takes, every bit of data it transmits, adds to our understanding of the galaxy we inhabit and the conditions under which life might arise elsewhere. The wild discoveries about the heliopause are also forcing scientists to reconsider their models of how the solar system formed and evolved. The solar system is believed to have formed from a collapsing cloud of gas and dust about 4.5 billion years ago. That primordial cloud had a specific chemical composition, a specific density, and specific properties that influenced how the sun and planets formed. But where did that cloud come from? What was its history before it began to collapse? The answer is that it was part of the interstellar medium, part of the same vast reservoir of gas and dust that fills the space between stars. Understanding the properties of the interstellar medium today, through Voyager 1's measurements, provides insights into the environment from which our solar system emerged. The density, temperature, chemical composition, and magnetic field structure that Voyager is measuring are all clues to the initial conditions from which everything in our solar system ultimately derives. Of course, the interstellar medium has changed over the past 4.5 billion years. Stars have been born and died, enriching the medium with heavy elements created in their cores and scattered by supernova explosions. The galaxy has continued its slow rotation, mixing and churning the interstellar material. The local interstellar cloud that we're currently moving through didn't exist when the solar system formed. But by understanding the processes that shape the interstellar medium today, scientists can build better models of how it behaved in the distant past. The magnetic fields that Voyager 1 is measuring are particularly important for understanding star formation. When a cloud of gas begins to collapse under its own gravity to form a star, magnetic fields can resist that collapse, threading through the cloud and providing support against gravitational compression. The strength and structure of the magnetic field help determine whether a cloud will collapse quickly to form a massive star or slowly to form a smaller star, whether the resulting star will have a planetary system, and what the properties of that planetary system will be. Voyager 1's measurements show that the magnetic field in the local interstellar medium is stronger than some models predicted, with field strengths of a few microgauss. A microgauss is an incredibly weak magnetic field by everyday standards, about 1/1,000,000th the strength of Earth's magnetic field at its surface. But in the diffuse environment of interstellar space, even such weak fields can have important effects, influencing the motion of charged particles and providing structure to the plasma. The orientation of the magnetic field is also revealing. As mentioned earlier, the field appears to run roughly parallel to the heliopause, rather than being oriented in the direction predicted by some galactic magnetic field models. This suggests that either our models of the galactic field are wrong, at least in the local neighborhood, or that the heliopause itself is influencing the field, perhaps draping it around the heliosphere in a way that changes its local orientation. Distinguishing between these possibilities will require more data, perhaps from future missions that venture even farther into interstellar space or that approach the heliopause from different directions. The velocity measurements that Voyager 1 has obtained paint a picture of an interstellar medium that is far from static. The local interstellar cloud is moving relative to our solar system at a speed of approximately 52,000 miles per hour. This might sound incredibly fast, and by terrestrial standards it certainly is, but in the context of galactic dynamics, it's actually a relatively modest velocity. The motion reflects the overall rotation of the galaxy and the peculiar motions of different clouds and structures within the interstellar medium as they respond to gravitational forces, pressure gradients, and the expansion of supernova remnants. What makes this velocity particularly interesting is that it's not uniform throughout the cloud. Voyager 1's measurements suggest variations in the flow velocity, evidence that the cloud has internal structure, regions where material is moving slightly faster or slower, converging or diverging. These velocity variations can drive turbulence, create shock waves where fast-moving material runs into slower material, and generate the complex patterns of density and magnetic field that Voyager is detecting. Understanding these flow patterns is crucial for building accurate models of how interstellar clouds evolve over time. The flow of interstellar material past our solar system also has implications for the shape of the heliosphere itself. The heliosphere isn't spherical. Instead, it's elongated in the direction of the solar system's motion through the interstellar medium, somewhat like the shape of a comet with a rounded head and an extended tail. The side of the heliosphere, facing into the oncoming interstellar wind, is compressed, while the trailing side is stretched out into a long heliotail that extends potentially hundreds of billions of miles downwind from the Sun. Voyager 1 crossed the heliopause on the nose of the heliosphere, the side facing into the interstellar wind, where the boundary is closest to the Sun. Its sister spacecraft, Voyager 2, crossed the heliopause in a different location, in a different year, and measured slightly different properties of the boundary region. The differences between what the two spacecraft measured are helping scientists map out the three-dimensional structure of the heliopause and understand how it varies with position and time. Voyager 2's crossing of the heliopause in November 2018 provided crucial confirmation of Voyager 1's earlier findings, while also revealing new complexities. The two spacecraft encountered different magnetic field orientations, different plasma densities, and different levels of turbulence at their respective crossing points. This isn't surprising given that they crossed at different locations and at different times in the solar cycle, but it demonstrates just how variable and dynamic the boundary region truly is. The heliopause isn't a fixed surface, but rather a constantly shifting zone that responds to conditions on both sides. The fact that we have two spacecraft sampling interstellar space from different vantage points is extraordinarily valuable for scientific research. It's like the difference between viewing a sculpture from one angle versus walking around it and seeing it from multiple perspectives. Each viewpoint reveals details that weren't apparent from the other, and together they provide a much more complete picture than either could alone. Scientists can compare the measurements from the two Voyagers, look for similarities and differences, and use those comparisons to test their models of heliospheric structure. The energy spectrum of the cosmic rays that Voyager 1 is measuring extends across an enormous range, from particles with energies of a few million electron volts up to billions of electron volts. An electron volt is the amount of energy an electron gains when accelerated through an electric potential of 1 volt, a tiny amount of energy by everyday standards, but a useful unit for describing particles in space. The cosmic rays Voyager detects span this huge range because they come from multiple sources and have been accelerated by different processes. The lowest energy cosmic rays in interstellar space are typically particles that were accelerated relatively recently and haven't traveled very far from their source. They might come from nearby supernova remnants, or from the acceleration processes at the heliopause itself. These particles have energies of millions or tens of millions of electron volts, making them relatively easy to detect and study. Higher energy cosmic rays, with energies in the billions of electron volts and beyond, are rarer but carry much more energy. These particles have likely been accelerated by more powerful sources and may have traveled across significant portions of the galaxy before reaching Voyager's location. By measuring the energy spectrum, the distribution of how many particles have different energies, scientists can learn about the acceleration mechanisms that produce these cosmic rays and about the processes that have modified the spectrum during the particle's journey through space. A steep spectrum, where low-energy particles vastly outnumber high-energy ones, suggests recent acceleration or significant energy losses during propagation. A flatter spectrum, where high-energy particles are relatively more abundant, might indicate very efficient acceleration or a population of particles that has diffused through the galaxy for a long time, with the low-energy particles having been preferentially lost along the way. Voyager 1 has observed that the cosmic ray spectrum in interstellar space doesn't match a simple power law, the mathematical relationship that describes many cosmic ray populations. Instead, there are bumps and features in the spectrum, excesses of particles at certain energies and deficits at others. These features are clues to the detailed physics of cosmic ray acceleration and propagation, and researchers are working to understand what they reveal about the sources and history of the particles Voyager is detecting. The composition of cosmic rays is equally revealing. By identifying which atomic nuclei are present in the cosmic ray population and in what abundances, scientists can trace the cosmic rays back to their sources. For example, cosmic rays rich in heavy elements like iron and nickel likely originated in supernova explosions, where these elements are synthesized in the final moments of a massive star's life and then ejected into space. Cosmic rays dominated by hydrogen and helium might have been accelerated from the ambient interstellar medium or from stellar winds. Voyager 1's cosmic ray subsystem can identify different nuclear species, allowing scientists to measure the composition of the cosmic ray population in interstellar space. The measurements show a composition broadly similar to the composition of material in the interstellar medium, with some notable differences. Certain elements are enhanced relative to their average abundance in space, suggesting they've been preferentially accelerated, or that the cosmic rays Voyager detects come from sources with unusual compositions. Untangling these effects requires comparing Voyager's measurements with observations of cosmic rays near Earth, and with models of how cosmic rays propagate through the galaxy. One particularly interesting class of cosmic rays consists of radioactive nuclei, atomic species that decay over time. When cosmic rays are accelerated at their source, they may include freshly created radioactive isotopes. As these particles travel through space, the radioactive nuclei gradually decay, transmuting into other elements. By measuring the abundance of radioactive isotopes in the cosmic ray population and comparing it to the abundance of their stable decay products, scientists can estimate how long the cosmic rays have been traveling since they were accelerated. This provides a cosmic clock, a way of determining the age of the cosmic ray population. The measurements are challenging because radioactive nuclei are rare in cosmic rays to begin with, and detecting enough of them to make statistically significant measurements requires long observation times and sensitive instruments. Voyager 1 has contributed to these measurements, though the definitive work on cosmic ray ages has come from a combination of Voyager data and observations from other spacecraft and from detectors on high-altitude balloons and at ground-based observatories. The consensus is that most cosmic rays have been traveling through the galaxy for millions of years, bouncing back and forth in the galactic magnetic field, gradually making their way from their sources to our location in space. The isotopic composition of cosmic rays can also reveal information about nucleosynthesis, the processes by which elements are created in stars and stellar explosions. Different fusion reactions and different explosive environments produce different isotopic ratios, different proportions of isotopes of the same element. By measuring these ratios in cosmic rays, which sample material from throughout the galaxy, scientists can test their models of stellar evolution and supernova physics. Voyager 1's measurements, combined with data from other missions, have helped refine our understanding of these processes. The electrons in the cosmic ray population deserve special mention because they behave quite differently from the heavier atomic nuclei. Electrons are much lighter than protons or heavier ions, which means they lose energy more quickly as they propagate through space. When an electron moving at high speed encounters a magnetic field, it radiates energy in the form of synchrotron radiation, electromagnetic waves that carry away the electron's kinetic energy. This process limits how far high-energy electrons can travel from their sources. The presence of high-energy electrons in the cosmic ray population detected by Voyager 1 therefore indicates that there must be relatively nearby sources of electron acceleration. These sources are probably not the same as the sources of the heavier cosmic ray nuclei. Supernova remnants can accelerate both electrons and ions, but certain other acceleration sites, like pulsar wind, nebulae, or the jets from active galaxies, might preferentially produce electrons. The energy spectrum and intensity of cosmic ray electrons that Voyager measures help constrain where these sources are located and how powerful they are. Another wild aspect of Voyager 1's journey involves the gravitational environment the spacecraft is experiencing. We tend to think of gravity as the dominant force in the universe, the force that holds planets in orbit around stars and stars in orbit around the galactic center. But at Voyager 1's current distance from the Sun, solar gravity is extraordinarily weak. The gravitational pull that the Sun exerts on Voyager 1 is now less than 1/10,000,000th of the gravity we experience on Earth's surface. It's still enough to very gradually slow the spacecraft down, but the effect is minuscule compared to the spacecraft's outward velocity. This weak gravitational environment means that other forces can become relatively more important. The pressure from sunlight, for instance, though incredibly tiny, is actually comparable to the gravitational pull at Voyager's distance. The spacecraft is so far from the Sun that even the faint pressure from solar photons can have a measurable effect on its trajectory. Engineers have to account for these subtle forces when planning the spacecraft's long-term trajectory and when calculating how much fuel remains for attitude control maneuvers. The gravitational influence of other stars is also starting to become relevant, not in terms of actually affecting Voyager's trajectory over the mission's remaining lifetime, but in terms of what will happen to the spacecraft in the distant future. As Voyager 1 continues its journey for thousands and millions of years, it will gradually fall under the gravitational influence of other stars in our galactic neighborhood. Computer simulations of Voyager's trajectory suggest that in about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445, a red dwarf star in the constellation Camelopardalis. That's the closest approach to another star that Voyager 1 is predicted to make for at least the next several 100,000 years. Even at that closest approach, Voyager 1 will still be incredibly far from Gliese 445, far enough that the star's gravity will barely deflect the spacecraft's path. But over millions of years, the cumulative effects of many distant stellar encounters will gradually alter Voyager's trajectory, causing it to wander through the galaxy in a complex path that's essentially impossible to predict with any accuracy beyond a certain point. The spacecraft will become a perpetual wanderer, a silent monument to human curiosity drifting through the cosmos long after humanity itself may have ceased to exist. The longevity of Voyager 1 as a physical object is worth contemplating. In the vacuum of interstellar space, there are no weathering processes like those that erode structures on Earth. There's no oxygen to cause rust, no water to cause corrosion, no wind to sandblast surfaces, no biological processes to break down materials. The main threats to Voyager's physical integrity are impacts from dust grains and the cumulative effects of radiation damage to its materials. Dust impacts are a concern, but the density of dust in interstellar space is extremely low. Voyager 1 is traveling at about 38,000 miles per hour relative to the interstellar medium, which means that even tiny dust grains hit with considerable energy. Over millions of years, countless impacts from microscopic particles will gradually erode the spacecraft's surfaces, pitting and cratering the exterior. But the spacecraft is sturdy, built to withstand the harsh environment of space, and it will likely remain largely intact for millions of years, even as its surface is slowly worn away. Radiation damage is more insidious. High-energy cosmic rays passing through the spacecraft's materials can displace atoms, breaking chemical bonds and altering the structure of metals, ceramics, and other substances. Over time, this damage can cause materials to become brittle or to change their properties in other ways. But again, the process is extremely slow, and the spacecraft should remain structurally sound for far longer than its electronic systems will continue to function. The golden record itself is designed to last for an extraordinary length of time. The record is made of gold-plated copper, materials chosen specifically for their resistance to corrosion and their longevity in the space environment. The information is encoded as physical grooves on the record's surface, an analog storage method that doesn't degrade the way magnetic or electronic storage does. Short of a catastrophic impact that physically destroys the record, the information should remain readable for hundreds of millions of years, perhaps even billions of years. By the time the record becomes unreadable due to erosion or damage, our sun will likely have evolved into a red giant, potentially engulfing the inner planets, and our entire solar system will have been transformed beyond recognition. The philosophical implications of Voyager 1's journey are profound and worth considering. This spacecraft, this machine built by human hands and human minds, will outlast not just every person alive today, but every person who will ever live. Unless we develop technologies we can scarcely imagine, it will outlast our cities, our monuments, our languages, our cultures, potentially even our species. Long after the last human has spoken the last word in the last human language, long after Earth itself may have become uninhabitable, Voyager 1 will still be sailing through the galaxy, carrying with it the golden record, a testament to what we once were and what we once hoped to become. Carl Sagan spoke eloquently about this in his reflections on the Voyager mission. He noted that the spacecraft represents a kind of immortality, not for any individual human, but for humanity as a collective. As long as Voyager exists and carries the golden record, something of human civilization will persist in the universe. The music, the voices, the images encoded on that record will continue to exist, waiting in the silence of space for the unimaginably remote possibility that some other intelligence might one day find them and learn that we existed, that we created art and music, that we gazed up at the stars and wondered if anyone else was out there looking back. But we don't need to wait for some hypothetical alien civilization to appreciate the significance of Voyager's journey. The wild discoveries the spacecraft is making right now, the data streaming back across the light hours that separate us, are expanding human knowledge and deepening our understanding of the universe we inhabit. Every measurement Voyager 1 takes is a gift to future generations of scientists, students, and curious individuals who will build upon this foundation of knowledge, using it to inform their own explorations and their own attempts to answer the fundamental questions of existence. The data archive from Voyager 1 is carefully preserved and made available to researchers around the world. Anyone with the appropriate skills and interest can access the measurements, analyze them, and potentially make new discoveries that the original mission scientists never anticipated. This democratization of scientific data ensures that the mission's legacy will extend far beyond the working lifetime of the spacecraft, as new analytical techniques and new theoretical frameworks are applied to the observations. Educational institutions around the world use Voyager data to teach students about plasma, physics, space science, instrumentation, and data analysis. The mission serves as a case study in long-term project management, international collaboration, and the importance of basic scientific research. Students who learn about Voyager today may become the scientists and engineers who design and build the next generation of interstellar missions, spacecraft that will venture even farther into the galaxy and perhaps answer questions that Voyager's discoveries have raised. The technological legacy of Voyager is equally important. Many of the innovations developed for the Voyager mission have found applications in subsequent space missions and even in terrestrial technologies. The techniques for communicating across vast distances, for managing spacecraft with limited computational resources, for designing instruments that can survive for decades in the harsh environment of space, all of these have been refined and improved based on lessons learned from Voyager. The mission has trained generations of engineers and scientists in the art and science of deep space exploration. Looking forward, there are already discussions about future missions that could follow in Voyager's footsteps and venture even deeper into interstellar space. These proposed missions would carry more advanced instruments, capable of making measurements that Voyager cannot, and they would be designed from the outset for an interstellar mission rather than being extended far beyond their original objectives as Voyager has been. Some proposals envision spacecraft powered by nuclear reactors that could operate for centuries rather than decades, continuously transmitting data as they explore the galaxy. Others propose using solar sails or other advanced propulsion systems to achieve higher speeds, reaching the heliopause in years rather than decades, and then continuing onward to explore a larger volume of interstellar space within a human lifetime.